We are Team Good Vibrations.
In the United States, there are approximately 40,000 ambulances. These ambulances are all equipped with electrocardiogram technology used to monitor vital signs and diagnose heart conditions. However, these tests are often inaccurate and cannot be used for diagnosis or treatment. There is simply too much noise. Studies have shown that pre-hospital EKGs increase the survival rate of patients with heart conditions. Our mission is to reduce vibrational noise in transport to increase the number of diagnostically useful EKGs.
To solve this problem, we have developed and tested an in-ambulance floor stretcher suspension system. The stretcher is wheeled into our device and locked in place. Its forward and backward motion is smooth and reduced by springs, dampers, and linear bearings. While the end users of our product are the paramedics and EMS personnel driving the ambulance and transporting patients, our customers are ambulance owners and operators. Our estimate for the serviceable market is based on the number of ambulances operating in the United States today, the expected lifespan and price of our device, and an estimated adoption rate for our product. We estimate a total addressable market of $40 million annually and a serviceable market of $4 million annually. For our prototype, we decided to prove our concept using a scaled-down version of our device consisting of 2 linear bearings on rails, 8 springs, 1 damper, and a sorbothane padding for high-frequency vibration reduction. This prototype was a combination of the different technologies chosen to tackle the problem on a more manageable and cost-effective scale. Our prototype was fabricated with a high degree of skill and technique and produces high-quality data that validates our hypothesis.
In the following sequence, our team tested out 2 different types of motion that would occur on a normal ambulance ride. In the first clip, we tested out the effect of lower intensity vibrations and shocks, and in the second, high intensity impacts that could be caused by sudden braking or potholes. The next 3 diagrams show the results of our experiments. First of all, you can see what happened with the high intensity impact. The undamped impulse was actually an order of magnitude larger than the damped impulse. In the next diagram, you can see that when we shook the device, the jerk of the system was much higher when it was not damped, as you can tell by the more jagged, noisy curves. This removal of noise is a very good sign for our eventual EKG applications. And in what we call the undamped road trip, you can see what happens when a cart was pulled along with the prototype and the effective magnitude reduction in vibrational noise.